Welcome to Corning Optical Fiber's e-briefing on bend, bandwidth, or both, making the right choice for your enterprise network. My name is Sharon Bois, Product Line Manager for Corning's single-mode and multi-mode fibers, and I am pleased to be presenting this overview of the benefits of multi-mode fiber and why it is best suited for data centers and other enterprise network installations. As the presentation continues, you can pause, skip, or repeat slides by using the navigation buttons at the bottom of your screen. This presentation is broken down into two parts. Part 1 is an introduction to multimode fiber that covers bandwidth and the different designations for multimode fiber. Then we'll talk about the benefits of multimode fiber as compared to copper and single-mode fiber. Part 2 of the presentation will focus on the next generation application standards like 40 gig and 100 gig Ethernet. We'll also look at the latest multimode fibers such as OM4 and bend-insensitive multimode fiber like Corning's ClearCurve multimode fiber. To begin with, I want to be sure everyone understands the optical multimode, or OM, designations I'll be using to talk about different types of fiber during the presentation. These designations are set forth in the ISO IEC 11801 standard. Looking at the first two columns on this chart, you can see that OM1 is a 62.5 micron fiber. OM2, 3, and 4 are different grades of 50 micron fiber. You may have heard OM3 referred to as a 10 gig 300 meter fiber, and OM4 as a 10 gig 550 meter fiber. In columns 3 and 4, you can see the different bandwidth values, and that's really what differentiates the various types of 50 micron fiber. The different grades have very different effective modal bandwidth, or EMB values. These are the laser bandwidth values. They also have different OFL values, which are the overfilled launch, or LED bandwidth values. On the far right, you can see the 10 gig link lengths. We'll talk more about the different types of bandwidth values on the next slides. As I mentioned, bandwidth is the one area that differentiates the various types of 50 micron fiber. So let's take a deeper look at it. There are two different types of bandwidth. First, there's the overfilled launch bandwidth, or OFL, which represents how a fiber will perform when used with an LED light source. Whether you have a 50 micron or a 62.5 micron fiber, you're overfilling and lighting its entire core, and then you're measuring how quickly the light gets to the other end. That's fine when you're running LED systems at 10 or 100 megabits per second, but LEDs can only modulate to 622 megabits per second. Therefore, with 1 gig and higher speeds, you have to use a laser. A laser has a much smaller spot size than an LED, so you're not lighting up the entire core, and you need a different bandwidth measurement that better represents how your fiber is going to behave when you're using it with a laser. This brings us to the effective modal bandwidth, or EMB measurement, which was standardized in the early 2000s based on a DMD, or differential mode delay measurement. This measurement simulates an actual laser launch by distributing the power in a much more narrow region. Once you have collected the DMD data, you can do one of two things with this measurement. One is called mini-EMBc, and the other is called DMD mask. I'll get into some details on these measurements on the following slides. The DMD measurement works by scanning a very narrow 5 micron spot size laser across the center of the fiber at 1 to 2 micron increments. In the graph on the right, we're measuring the delay, or the amount of time it takes for the light to travel through the fiber depending on where it is launched. In a perfect fiber, you would see the nice tight pulse shown in the top line on the graph, and all of the pulses would be lined up underneath. This means that no matter where you launched light into that perfect fiber, all of the pulses would get to the end at the same time. The imperfect fiber in this illustration has quite a bit of differential delay because the pulse in the middle is significantly slower than the pulse on the outside. This DMD measurement is the same whether you are characterizing the fiber with DMD mask or mini-EMBc. It's what you do with this delay data that is different. In the DMD mask method, a mask, or template, is laid over the top of the delay pulses to evaluate the fiber. In order to utilize the masks, it is first necessary to get rid of any noise in the measurement using a level of 25% as provided in the standard. You can see that I've drawn a red box over part of the top pulse. That red box starts where the pulse reaches 25% of its total height and stops where it drops below the 25% line. By doing this, we are throwing away the data tails, and those pulses that originally were larger in terms of delay are now compressed a little bit. So with regards to the DMD mask characterization, this is the actual delay that we've recorded for this fiber. Next, we will try to overlay a mask on top of the delay pulses. The standard provides 6 masks for OM3 and 3 masks for OM4. This blue area represents one particular mask. It allows for different amounts of delay in different regions of the fiber. All of the red pulses need to fit inside the mask to be considered as passing. As long as the fiber passes one mask, it is considered OM3 or OM4 compliant. It can fail all of the others. If it doesn't pass any of the masks, it is considered OM2. DMD mask is the primary measurement Corning's competitors use when they evaluate their fiber. However, Corning looked at this measurement back in the early 2000s and determined that we really weren't comfortable that DMD mask was evaluating the fiber as rigorously as we thought was required. So we pushed for the development of a second standards-compliant measurement called min-EMBc. The min-EMBc measurement takes the same DMD data but works with it differently. You can see here that I've still got my 5-micron laser. I'm scanning across the center of the fiber's core and I'm recording my delays. However, we're not going to throw out any of the data. We're going to use that entire pulse to calculate an actual bandwidth value, which turns out to be 3,128 MHz/km. The standard defines 10 different VCSEL sources representing the edges of the allowable distribution for a high-speed VCSEL. These sources represent the worst cases you might see in a standards-compliant VCSEL in the field. With min-EMBc, we take the laser data, overlay it with these 10 different sources, and calculate 10 separate bandwidth values. For the sake of time and space, I'm going to show you just 3 on this slide. The red laser has slightly different characteristics. When this laser is paired with this fiber, there is more delay in the center region, so the bandwidth goes down. The green laser also has slightly different characteristics than the others, resulting in even more delay when paired with this fiber. And again, the delay translates into even lower bandwidth. In reality, we overlay 10 different lasers, calculate 10 different bandwidth values, and select the lowest to represent the minimum effective modal bandwidth. That is the one we report. You can think of it as having to pass all 10 in order to be standards compliant. There are a couple of benefits to this approach. One is that Corning reports an actual value, so you know if the fiber you're getting is just barely standards compliant, or if you have some extra bandwidth that you can use. Secondly, because it's the minimum value, there's a pretty good chance your fiber is going to outperform the reported value and provide you more bandwidth unless you happen to buy a laser that's exactly representative of the worst case scenario. In other words, min-EMBc gives you a very conservative measurement. I'm going to switch gears now and talk about where multimode fiber is used. As this illustration shows, multimode is really your in-building fiber. The campus backbone includes links that are connecting the different buildings in your network. You can see on the bottom of the slide that fiber is used the majority of the time in this area. There's really not a lot of copper anymore. The distances spanned in campus backbones are typically the longest in which multimode fiber is used. There are cases where single mode is definitely required, but a lot of the distances are still short enough that multimode fiber, even at 40 gigabit per second and 100 gigabit per second, is sufficient. Later, I'm going to show you that if you can use multimode fiber rather than switching to single mode fiber for these links, you can save money in your network. The next area we'll talk about is the in-building backbone, often called the riser, because the fiber rises up to each individual floor. Typically, this is a multimode fiber that connects to a telecommunications closet on each floor. The majority of this fiber is OM3, with some OM2 and OM4 being used as well. The next area is the horizontal. Known as the last run, this is where you take the fiber or copper from the telecommunications closet out to the desk. In fact, this is the area where copper is still largely used because it is generally capable of supporting the required speeds, which tend to be relatively low at 10 and 100 megabits per second. There may be some requirements for 1 gig, but not many. There are 2 areas in which the demand for fiber is growing in the horizontal. The first is organizations that are extremely concerned about security. Fiber is much more difficult to tap than copper. The Pentagon and other government-type installations, for example, have adopted fiber to the desk for security reasons. Second, we see growth in fiber to the zone systems. In these cases, you still bring fiber up the riser to the telecommunications closet, but instead of taking copper out to each individual workstation, you take fiber to several small telecommunications boxes throughout the floor. From there, you run copper to a smaller number of end users, so fiber is getting ever closer to the end user, and multiple copper runs are being shortened. The last area we'll talk about here are data centers, which will be the main focus of the rest of this presentation. Data centers are largely fiber-based to support speeds that are increasing significantly. We see 10 gigabits today, and demand is growing for 40 and 100 gigabit per second speeds. As a result, OM3 and OM4 multimode fibers are strongly preferred in this application. Now let's take a closer look at fiber versus copper. The charts on the right show the differences in 10 gigabit per second link lengths between the various types of fiber and copper. Obviously, fiber has greater capability if you need to go longer distances at 10 gigabits per second. There are many other advantages of fiber versus copper, which are listed on this slide. I'm not going to read through all of them, but I will point out a few. With fiber, you don't have to worry about electromagnetic interference, radio frequency interference, and crosstalk, which can be problematic with copper. In addition, fiber is much smaller and lighter, which is an advantage for installations and cable fuel loads. On the other hand, cost has typically been a bit of a challenge for fiber when compared to copper. To that point, if you last looked at fiber back when you were doing your 100 megabit per second or 1 gigabit per second installations, you probably saw that fiber was more expensive and may have decided to go with copper to save money. If you're now starting to think about 10 gigabit per second, I would encourage you to take another look at fiber because a lot of things have changed. For example, the comparison graphic on the right side of this slide shows the power consumption for a 10 gigabit per second fiber port versus a 10 gigabit per second copper port. You can see the 10 gig fiber port consumes about half a watt, whereas 10 gig copper consumes about 3 to 5 watts per port. General industry guidance is that every watt of power requires 1 watt of cooling. So when you factor that in, you're talking about a total of 1 watt for fiber and 6 to 10 watts for copper per port. That accounts for a pretty big difference in power consumption, cost, and being environmentally green. Another difference is the size of the transceivers. A fiber transceiver is significantly smaller than a copper one. This means the area required for a fiber data center can be substantially reduced, delivering additional cost savings. A third significant difference involves testing. With 10 gig copper, you start to encounter alien crosstalk testing. This refers to the fact that if you have a cable with a lot of different copper wires inside, you need to test each individual wire to see how it's going to interact with all of the other copper wires in that cable. Imagine a 144-wire cable and the huge number of hours it would take to complete that testing. By contrast, with fiber, even 10 gig fiber, you simply install it, conduct a point-to-point measurement, and you're done. The time savings can translate into significant cost savings if you choose fiber. To explore the potential savings for your network, you can download the free cost model available on www.foles.org. It allows you to compare different fiber versus copper scenarios and the related costs. Earlier, I said you can save money if there's an opportunity for you to use multimode fiber instead of single-mode fiber, and now I'd like to show you how. This pie chart shows what contributes to the total cost of a typical 300-meter backbone. The biggest part is the fixed cost for the switch electronics. This represents about 3/4 of the total cost of the system, and it's virtually the same whether you install single-mode fiber or multimode fiber. So this part is not particularly interesting for this kind of analysis because it doesn't change. What is interesting is the other 1/4 of the pie. As you can see, transceivers are the dominant component. The fiber optic cable, jumpers, and patch panels combined represent only about 2 to 3% of the total system cost. So even though you're going to spend a little bit more for your multimode fiber or your multimode cable, it's only 2 to 3% of your total cost. If you look at the dominant transceiver piece, then single-mode transceivers for 10 gigabit per second are 2 to 3 times more expensive than multimode transceivers. And when we talk about next-generation speeds like 40 gigabit per second and 100 gigabit per second, that difference is expected to grow. Current projections for 40 gigabit per second are that single-mode transceivers will be about 4 times the cost of multimode transceivers. And for 100 gig, single-mode transceivers are anticipated to be 10 to 11 times more expensive. The bottom line is, even though you're paying a little more for the fiber and cable, it's such a small piece of the total pie that you can save 2 to 3 times or 4 to 10 times for next-generation speed transceivers. That means your total system costs are going to be less with multimode fiber. There are also significant differences in the power requirements for 40 gigabit per second and 100 gigabit per second single-mode transceivers compared to multimode transceivers, making multimode fiber networks even more attractive at higher speeds. Here's a specific example of that scenario. The chart shows OM2, 3, and 4 multimode fibers, which are the different 50-micron types we've been talking about. In addition, it shows an OM2 LX. LX represents long wavelength, or 1300 nanometer operation, and an OS2 LX, where OS stands for optical single mode. The comparison is for a 300-meter network operating at 1 gigabit per second. Now let's take a look at costs. If we just look at the fiber and cable components, we see that OS2 single-mode fiber is the least expensive, followed by OM2, 3, and 4. However, adding in the hardware costs makes a difference in that single-mode connectors are much more expensive than multi-mode connectors, and there is more time involved in connectorization. That's because single-mode fiber has a much smaller core size, making alignment much more difficult. So once the hardware is added, the single-mode fiber and OM2 fiber systems are roughly the same cost, but you're still paying a premium for OM3 and OM4. Now look what happens when I add in the transceivers using a 2x multiplier. I mentioned before that this could be 2 to 3 times more expensive for 10 gigabit per second and significantly more for 40 and 100 gigabit per second. You can see here that the single-mode fiber and long-wavelength multimode fiber solutions are quite a bit more expensive than the different grades of multimode fiber operated at their primary wavelength of 850 nanometers. OM2 is still the least expensive solution, but there is only a 10 to 20% premium for OM3 and OM4 in order to get a 10 gigabit per second upgradable capability. The analysis on the previous slide was based on 1 gigabit per second because that is still the port size used most commonly today. While you hear a lot of talk in the market about 10 gigabit per second, the reality is that while people are installing 10 gig ready systems, they're still using 1 gig ports. I'm demonstrating here that even if we switch and look at 10 gig, the 2 to 3x multiplier for 10 gig transceivers is still maintained. And although 1300 nanometer costs continue to come down, 850 nanometer costs do as well, and you continue to see that 2 to 3x delta. Based on this, we really don't expect a change in the cost savings of multimode fiber as compared to single-mode fiber for short-distance networks. The relatively inexpensive upgrade path provided by OM3 and OM4 fiber is driving purchase behavior for different types of multimode fiber. This chart is based on North American data taken from the Burroughs Report. Each of the individual cablers in North America submit their sales to Burroughs on a quarterly basis. Those numbers are combined and sent back to each contributor, providing a macro view of what's going on in the market. Here you can see the trend for 50 micron versus 62.5 micron going back to 2005. At that time in North America, the vast majority of demand was for 62.5 micron. Look at how quickly that's been changing. Since the first quarter of 2008, we've been seeing more 50 micron sold in North America than 62.5 micron, and that conversion rate just continues to increase. Today, only about 35% of demand is for 62.5 micron, and we expect it will continue to drop in the coming years. If you looked at this graph in other regions, you would see an even quicker transition over to 50 micron. That's because those regions decided to go with 50 micron from the beginning, while North America embraced 62.5 micron. In that sense, they were much further along the curve at the outset, and there's significantly less 62.5 micron being used outside of North America. If we take that 50 micron multimode fiber demand and break it into OM2 versus OM3 and OM4, which are your laser optimized 50 micron fibers, you can see a similar trend. In the beginning of 2005, the majority again was OM2, but since 2007, we've been selling more of the OM3 and OM4 laser optimized multimode fibers than the standard OM2. Again, that demand is increasing, and we expect it to continue. The trend is similar in other regions. At this point, I'd like to summarize the key points I've made about multimode fiber. Looking at the single mode column in the table, we can see that you can carry more information and support longer distances with this type of fiber. If you only consider the fiber price or the combined fiber and cable price, single mode is definitely less expensive. However, when you add the connector and transceiver price differences and consider that multimode is easier to handle because of its core size, it becomes clear that multimode is the lowest price system for shorter lengths, like 10 gigabit per second up to 550 or 600 meters. Single mode fiber at 10 gigabit per second is the best choice for 600 meters or further. The information at the bottom of the slide comes out of the TIA, Telecommunications Industry Association, and IEC, International Electrotechnical Commission standards. So it's not just Corning or other manufacturers saying that you should use multimode fiber. The standards organizations support this view as well. They recommend the use of laser-optimized 50 micron multimode fiber for backbone cabling because it's capable of supporting higher speeds over longer distances and is more cost-effective than single-mode fiber. Now let's talk about next-generation multimode fibers and standards. I'll talk about OM4 and next-generation speeds first, and finish the presentation with an overview of Corning's ClearCurve multimode fiber. OM4 is the latest generation of multimode fiber. As I mentioned previously, it's a 50 micron high bandwidth multimode fiber capable of supporting higher bit rates, longer link lengths, and more margin for additional connectors. I showed this chart earlier in the presentation. Here I have added the 100 gig link lengths for comparison purposes. As you can see, OM4 will enable 150 meters at 100 gigabits per second. The OM4 standard was approved in August of 2009, but it's not really a new fiber. An OM4 type fiber has been sold by most of the major fiber manufacturers since 2004-2005. For example, many of you may have been buying an OM3 Plus or a 10 gig 550 meter fiber for several years. It is important to understand that 40 and 100 gig speeds involve a different way of transmitting data over multimode fiber. The standard is based on the concept of parallel optics. As a frame of reference, a 1 gig system uses a 1 gig transceiver and one fiber transmitting 1 gig per second to the receiver at the end. The same is true with 10 gig. The system includes a 10 gig transceiver and one fiber transmitting 10 gig to the receiver at the end. With 40 and 100 gig, it's a different story. Currently, VCSELs can't modulate up to 40 and 100 gigabit per second, so it was necessary to develop another way of achieving these speeds. The solution was parallel optics, which is based on VCSEL arrays. For a 40 gig system, a VCSEL array has 4 fibers transmitting over 4 10 gigabit per second transceivers, which are combined at the end to get 40 gigabits per second. The same is true on the receiver side, where there are 4 transmitters sending the information back over 4 fibers and receiving and combining it at the end. So you really need 8 fibers when you're talking about 40 gigabits per second transmission. And for 100 gigabits per second, the array includes 10 VCSELs and 10 fibers to transmit and another 10 fibers to receive, or 20 fibers total. Let's take a look at the OM3 and OM4 distances included in the 40 and 100 gigabit per second standards. They are marked in bold on the screen, and as you can see, the standard is 100 meters over OM3 and 150 meters over OM4 for both speeds. You're probably used to the distances being different for various speeds. However, that is not the case for 40 and 100 gig speeds because of parallel optics. As the arrays on the previous slide showed, both 40 and 100 gig are based on 10 gig transmission, so the distances are actually the same. I also want to point out the copper distance in this standard. As you'll recall in a previous slide, we showed that some types of copper were capable of supporting up to 100 meters at 10 gigabits per second. When it comes to 40 and 100 gig, however, copper can only support 7 meters. Interestingly, when they started developing this standard, copper was set at 10 meters. However, they weren't able to prove capability to 10 meters, so the copper standard was reduced to 7. This means there's quite a big gap now that multimode fiber needs to fill, and that is one of the things that drove the transceiver design. There was a lot of interest in getting the transceivers to be as inexpensive as possible. A lot of the transceiver specifications were loosened so the manufacturers can keep their yields up and their costs down, even though they were making this array of 4 or 10 10-gig transceivers. You'll see the impact of that on the next slide. One question I'm frequently asked is, what's the value of OM4 compared to OM3? And is OM3 still going to be a future-proof solution? My answer is, it really depends on what you need in your system and what type of application you're using. This graph shows the distance that's going to be supported by different bandwidth values for various application speeds. If you look at the x-axis, laser bandwidth starts with OM3 on the left and goes up to OM4 on the right. Link lengths are shown on the y-axis. Let's start with the 10 gig Ethernet application, as that's probably the one you're most familiar with. As you can see, it's capable of supporting 300 meters on OM3 and 550 meters on OM4. So if you ask me the value of OM4 for a 10 gig installation over extended distances, I'd say there's definitely quite a bit of value for OM4, depending on how far you're looking to go. Now let's look at the other extreme, which in this case would be a 4 gig fiber channel. The 4 gig fiber channel standard includes a loosely specified transceiver with a very broad spectral width, which makes for a dispersion-limited system. So, while it is possible to go 380 meters on OM3, you can only go to 400 meters on OM4. All of that additional bandwidth only gets you 20 meters. So if you ask me the value of OM4 for a 4 gig system, I'd say you can get 380 meters with OM3. And unless you're trying to go 390 or 400 meters, there's really not a lot of value in installing an OM4 fiber. The key thing to remember here is that it's not just about the fiber. You need to understand the transceiver that you're using as well. The combination of the transceiver and the fiber will dictate how your system behaves and what your system is capable of doing. That brings us to the next generation speeds, which are 16, 40, and 100 gig. 16 gig still uses serial transmission with one transceiver and one fiber, not parallel optics. Therefore, in order to transmit at 16 gigabits per second, the VCSEL manufacturers had to tighten up the spectral width. The impact is that for 16 gig, OM3 goes 100 meters, and OM4 can go 125 meters. So there's a 25% benefit with OM4 fiber as compared to OM3 for 16 gig. With 40 and 100 gig, it's a similar story. Another question I get frequently is, if 40 and 100 gig are based on 10 gig optics, why aren't we talking about 300 meters on OM3 and 550 meters on OM4? The answer is the specifications were significantly loosened to keep the yields up and the costs down. So with parallel optics VCSEL arrays, it's now possible to get 100 meters on OM3, and if you tighten up the connector loss, you can get 150 meters on OM4, which is a 50% gain in distance. As you can see, there's definitely value in OM4, but you can't reach the same distances as you can with a single 10 gigabit per second transceiver because of the different specifications for 40 and 100 gigabits per second. What does that mean for OM3 and OM4 where you're using it today? This graph shows cable links that we would see in a data center application, which is where the majority of 40 and 100 gig will be rolled out in enterprise networks. About 70% of the links are 100 meters or less. Therefore, OM3 fiber paired with standard 40 or 100 gig transceivers will meet your needs 70% of the time. One thing to note is that OM3 and OM4 link lengths were specified with different levels of connector loss in the standard. If you reduce the connector loss on OM3 fiber to the same 1 dB level that's standard for OM4, you can support 120 meters on OM3, which gets you to about 80% of the links. At 150 meters, OM4 fiber covers about 90% of the data center links. This means the inexpensive transceiver that allows you to compete with copper and pick up all those short lengths at an inexpensive cost is going to work for 90% of users. That's great, but 10% still need another solution. The good news is the fiber itself, whether OM3 or OM4, is very capable. You just need to increase the capability of the transceivers. One way to do this is to tighten up the spectral width. Another option is to add a chip to the transceiver, such as a forward error correction chip known as FEC or a clock data recovery chip known as CDR. Any of these options allow you to increase the OM3 and OM4 distances to exceed what is currently specified in the standard. To illustrate this point, Corning did a demonstration a couple of years ago at an Interop conference. We bought a commercially available 40 gigabit per second transceiver and paired it with Corning fiber and cable to see how far we could go. We were able to get to 250 meters on OM3 and 350 meters on OM4. So it's definitely possible to go further than 100 or 150 meters. It just depends on the specific transceiver that you're using. To wrap up today's presentation, I'm going to talk about Corning's ClearCurve multimode fiber. This bend-insensitive multimode fiber is one of our latest innovations. You may ask, why do we need a bend-insensitive multimode fiber? In an initial installation, people generally follow the rules, and everything looks perfect and pristine. And you could argue, from a fiber, cable, and loss perspective, that there's really not much value installing a bend-insensitive multimode fiber. But the problem is, most systems don't look pristine for long. Invariably, there will be moves, adds, and changes that cause the original installation to become a jumbled mess. This is when a bend-insensitive multimode fiber really adds value. As Corning developed ClearCurve multimode fiber, we spoke with many data center managers to understand their challenges and what they wanted a new fiber to address. We learned they were looking for increased density, improved slack management, reduced congestion in pathways and spaces, and improved airflow. A bend-insensitive fiber addresses all of these requirements because it enables a smaller cable design and the ability to wrap the slack tighter. In addition, the data center managers we talked to indicated they needed help with some of their polarity concerns, as well as improving moves, adds, and changes. And once again, bend-insensitive multimode fiber does the job. Think about a typical data center installation. You've won a bid. You're starting to think about what you might want to put in there. Chances are, cabling is not going to be your first thought. Rather, you're thinking about what kind of systems, PCs, and software you're going to use, because that's where the majority of your capital investment is going to go, as shown by the blue bars in this chart. But when you get all of your equipment, you realize you need something to connect it all together, and that's where cable comes in. The green bars on the graph show that cable actually has the longest expected lifetime of all of the system components. For this reason, it's important to spend time up front designing your system and investing in a future-proof cabling infrastructure that will support your installation. If you don't, you could end up in a situation where cabling is one of the most expensive parts of your network. Why? Because cabling can have the highest potential for network failure since it's in the system for so long. Choosing a cable made with a bend-insensitive fiber like ClearCurve multimode fiber can help ensure this doesn't happen. How does bend-insensitive multimode fiber work? Multimode fiber has a number of different modes traveling through the fiber. This means there are many paths light can take to get to the end. The modes that travel along the outer edge of the fiber are loosely guided, and when you bend a typical multimode fiber, the light wants to keep going in a straight line, and some of these loosely guided modes can escape outside the core. When that happens, you have bend-induced attenuation. A bend-insensitive multimode fiber, like Corning's ClearCurve multimode fiber, has an optical trench outside the core that acts like a wall or barrier. So when you bend the fiber and the light tries to escape, it effectively hits the trench and is forced to stay inside, resulting in a significant reduction of bend loss under tight bend scenarios. This graph shows a standard OM3 or OM4 fiber compared to a ClearCurve OM3 or OM4 fiber in different bend scenarios. You can see that regardless of the bend radius, you get about 10 times lower bend loss with ClearCurve multimode fiber. In addition to improved bend performance, ClearCurve OM3 fiber has the high bandwidth that you need, delivers improved opticals, and is fully standards compliant. Also, it is compatible with the existing installed base of 50 micron standards compliant fiber, and you can splice it and connectorize it with commercially available equipment. The chart at the bottom of the slide shows different multimode bend standards. You may notice that multimode is pretty far behind single-mode fiber when it comes to bend standards. Single-mode fiber has a 10 mm bend standard, a 7.5 mm bend standard, and even a 5 mm bend standard. For a long time, multimode had just a 37.5 mm bend standard, which is like the radius of a baseball, a pretty big bend. A few years ago, ITU standardized the loss for a multimode fiber with